name is Eray. Today I'll be talking about the near-surface geophysical investigation of the 2010 Haiti earthquake epicentral area. Let's go ahead and start. Here's my outline. On the introduction section, I'll be explaining you what the problem is and what my objectives are. Following the introduction, I'll be showing you I'll be explaining about why we selected that specific area for our survey. It's basically Leogan area. On the next section, I'll be showing you some of the results that we have obtained so far from 2012 and 2013 surveys. In the last section, I'll be integrating all these results to come up with an integrated analysis for the near surface. Let's go ahead. First, let's actually step back and think about where we are and where is Haiti. So we're in Houston. If you go about 900 miles to southeast, you'll find this beautiful island called Hispaniola. The western part of this island is Haiti, and we're only 900 miles away from this major plate boundary between North American plate and Caribbean. So the Haiti project in 2010, there was a major earthquake, 7.0 magnitude earthquake. Unfortunately, more than 200,000 people have died in this earthquake. What we knew about this area is that there's two major strike slip fault, one in the south, one in the north. The one in the south is called the Enriquillo fault. And from the historic records, it has been proven that this strike slip fault is capable of producing one major earthquake per century. And right after the earthquake, the epicentral studies were actually suggesting a location around the Leogan area. But the surface expression of this fault was never found, so this was very interesting. The recent studies are now suggesting that there might be a neighboring blind fault in this Leogan area called Leogan fault, which brings us to our objective. So our objective is to characterize and analyze the near-surface structure. Measuring this near-surface sediment properties are very critical for geotechnical studies. Of course, we're attempting to find this blind fault. By doing all of these, we should provide a better understanding of the local geology of this region. One of the critical questions is that, why we selected this Leogan area for our surveys, besides being the epicenter location. So most of the recent studies are concentrated in here, and they came up with some suggested models. On the right side, you're seeing a model suggested by remote sensing data. The red plane in here represents the overall geometry of the main Enriquillo fault. So we're now talking about the strike slip fault. So it's dipping towards south. It's actually quite steep, about 70 degrees. The blue plane in here represents the proposed blind fault geometry. It's dipping towards north with about 40 to 45 degrees. You're seeing a seismicity map that was recorded right after the earthquake. These mini dots represents the mini earthquake locations. They're actually color-coded according to their depth. We're mostly concentrated on the Leogan area, so let's look at the C to C prime line. What you're seeing here is actually a pretty good line that appears to be dipping from C to C prime. C prime is the north, so we might be seeing hints of this proposed blind fault, and you can even make an argument that it appears to be that it's dipping somewhere between 40 to 60 degrees. Before getting into detail about the seismic data, I just wanted to quickly go through the lab measurements. We have acquired several number of rock samples. Unfortunately, none of these are exactly on the survey location because the absence of the outcrop. Sample A and C collected about 20 kilometers away. Sample B is collected about 5 kilometers away. You're seeing the results from these rock samples. We have identified sample B as a layered limestone. There's a quite bit of change on the P-wave velocities on different axes. So these are the P-wave values, these are the shear wave values, and this is the density value, 2.0 grams per cc. And then what I've done is that I try to apply simple Gardner relationship calculations to come up with an estimated result by using the P-wave from the seismic studies. So I have a little bit of difference between estimated and measured. These values are not the same. The weathered structure of my sample or the rough approximation from the Gardner relation could be the reason for this mismatch between estimated and the measured density. From now on, I'll be talking about our surveys in the Leogane area. On the left, you're seeing a digital elevation map. The hot colors represent the relatively elevated areas, and the green and cool colors are pretty much the flat areas. In 2012, we have acquired line A with a hammer source. This was an initial survey. In 2013, we acquired line B, C, and this longer line D. There's something important about line C is that it's a horizontal line. We used slanted accelerated wave drop to generate shear waves, and we had our shear wave geophones, the horizontal geophones in here. These are some of the pictures that we have taken in the field. As you can see, the topography is quite flat, and we were always welcomed by the locals. And this is our accelerated wave drop system oriented in a slant. It's slanted to generate the shear waves. Now I'll be showing you the results from the P-wave refraction studies from line A and B. I've generated an 80-meter deep model. The hot colors represents higher velocities, and cool color represents the lower velocities. On both of these models, what you're seeing in here is that these low velocity layers on top appears to be getting thicker towards south. It's not a big difference, but they appear to be getting thicker towards south on both of these models. And we're also seeing what appears to be a boundary between these low velocity layers on top and relatively higher velocities on the bottom at about 50 meters. The next study is to generate a shear wave images from ground roll inversion. If you have any questions about this technique, I can talk to you after the presentation. The cool colors represents the low velocities. Line A is located right on the beach, so overall we're seeing very low velocities on line A. Line D is plotted in here. We're seeing some anomalous response on line D, having these high velocity structure on top of low velocities. I'll be talking more details about this anomalous response. Line B and D actually has an overlapping zone. This box represents the extension of the line B. So line B is also giving pretty similar responses. Overall low velocities appears to be going underneath this relatively high velocity zone towards the south. What we have learned from these shear images is that an average velocity of 150 meters per second for the first 20 meters is actually, when you think about the soil classification, these are very low velocities. You can classify this soil as class E type or soft clay. And the soft clay, as you know, can result in liquefaction problems, and this might be the reason for the devastation at the nearest city. I'm still dealing with the line C shear wave, the horizontal line taking more time compared to the conventional P-wave lines. I just wanted to show refraction plots for two shots that are 250 meters apart. For the first 20 to 22 meters, we're seeing velocities between 110 to 140 meters per second. These are actually a pretty good match between the results we obtained from the ground roll inversion. So these two different approaches supporting each other in terms of the shear wave velocities. Here's the result from line A and B again for the reflections. On the right, you're seeing the time migrated section, and on the left, you're seeing the velocities. Time migrated sections revealed up to 350 meters. Similar to the refraction studies, we're seeing thickening of these low velocity layers towards the south, and over the seismic sections, we're seeing a lot of abruptions and discontinuities on the subsurface, maybe indications of some minor faulting, but nothing major. We're also seeing indications of channel bodies here, there, and some strong indications in here. So overall, we have observed low velocities. We also have seen the thickening of low velocities towards south. And on this line A, you can see the strong reflection at about 60 to 80 milliseconds, which I'll be talking about on the following slides. Now I would like to quickly go through the gravity analysis. The gravity stations are marked with a cross sign over line D. This is roughly a 4-kilometer line. Since this is only a 4-kilometer line, we're expecting to see somewhere up to 1.5 to 2 kilometer depth of investigation. So far from seismic, I've seen that these low velocity, possibly low density layers are getting thicker towards south. So I just wanted to model that. I just wanted to put that ID on my model and see whether I can obtain a good match between observed and calculated. So the dots represent my observed results, and the line represents my calculated response from the model. I have obtained pretty good match between those two with a 0.3 milligal difference. Basically, I'm just modeling the change of thickness in the fan sediments in these low density layers. And the mismatch between calculated and observed in this specific area could be due to the effects of local minor faulting. So far I have talked about the lab measurements, seismic data, and gravity data. Now I would like to put them all together to come up with an analysis for the near surface. So we already knew that this Enriquillo fault was dipping towards south. It is quite steep. If you go further north, you'll reach the ocean, and this is where we concentrated our studies in the Leogane area. From gravity, we have figured out that the Leogane fan is possibly getting thinner towards the north. Starting from this point, I'll be talking about the subsurface there. So my x-axis will be the distance and y-axis will be the depth. The refraction study is suggesting me that I have a boundary at about 50 meters, which separates these two different velocities, these low velocities on top and relatively higher velocities on the bottom. My reflection seismic is indicating that I have channel bodies, which is expected at this local region, at this local geology, and maybe some disruptions on the subsurface layer with minor faulting. That's what you're seeing here. And when you combine the lab measurements with these seismic results, actually what we're thinking is that the sample B, which is identified as limestone, has very similar velocities that we obtained from refraction studies, from seismic studies, that the top 550 meter could be these soft clay layers, seismic is slow velocity, and clay layers, and after about a 50 meter, we're getting into more relatively consolidated limestone layers. So that's about it. We have completed our 2012 and 13 surveys. The near surface, we believe, studies have provided very useful geotechnical information. These studies, actually these seismic lines were the first on-land reflection seismic data acquired in Haiti. We have tested the node system. For our future plans this year, within the next couple of months, we're planning to go back there and this time use a stronger source to image deeper sections actually in an attempt to find this blind fold at about 1 to 2 kilometer depth. And we would like to take the full advantage of using the node system to extend our lines. Thanks to Geospace for the donation. I would like to thank SCG, the SCG Foundation, Geoscientists Without Borders, AGL, Anouk William, Haiti Bureau of Mines and its employees, and JETCO for providing us the software. And I would like to thank you for listening to my talk. If you have any questions, I'll be more than happy to listen.